Hello, welcome to today's webinar, Oracle Active Data Guard with Axxana Phoenix for Disaster Recovery Zero Transactions Loss. My name is Melanie Brady and I will be your moderator today. Our speaker today is Dr. Alex Winokur. Dr. Winokur is Chief Technology Officer and co-founder of Axxana. Dr. Winokur is a world-renowned inventor in the areas of data management, data protection, and storage. Dr. Winokur has rich background in systems engineering and a proven record of developing high-performance, high-availability storage subsystems. Dr. Winokur is a strong leader with an established record of building R&D organizations and was named to CRN's 2010 list of storage superstars. Prior to co-founding Axxana, Dr. Winokur was CTO of XIV Information Systems, acquired by IBM, and founder of Cepiton, formerly Sandgate, a successful startup company in the area of storage area networks. Prior to that, Dr. Winokur spent 11 years in the IBM Research Division, achieving the prestigious title of IBM Master Inventor and authoring and co-authoring over 15 patents in the areas of storage, network management, and telecommunication. Dr. Winokur holds a Bachelor of Science and Master's of Science from Technion, Israel's Institute of Technology, and a PhD from Penn State University. Before we begin, I would like to remind the audience to please feel free to submit questions throughout the event via the question chat box on your webinar toolbar. Our speaker will leave some time at the very end of the presentation to address these. I would like to now turn the call over to today's presenter. Please go ahead, Dr. Winokur.
Hi, thank you for the introduction. So let's dive ahead and go to the next slide. Just a second. Why am I stuck here? Okay, let's go to the first slide. So what our product does. So as you will see our product together with Oracle Data Guard, we have developed a very unique solution which allows to do zero data loss recovery of data after a disaster, regardless of the distance between the sites, regardless of the nature of the disaster. It's a very cost-effective manner and with very high performance. So I believe this is probably the only solution in the world that can guarantee zero data loss recovery even if the distance between the two sides is hundreds of miles away. So what's the motivation behind the product? So what we have found out that everybody loves and would like to have zero data loss in case of disaster. However, everybody also wants geographic separation, which means that they would rather have quite a distance between the two sides so that one side is not affected by the disaster at the other side. The problem is that those two requirements don't mix together very well, because if you want zero transaction loss or zero data loss, you need a synchronous transport between the sites, and the distance, the long distances don't allow a synchronous transport because of the performance impact that mainly generates from the speed of light. So what's the motivation? So why people do want really zero data loss? So what we have found out that in mission critical applications, there is no such thing if you are doing an asynchronous or replication or you are in data guard asynchronous replication. There is no such thing as losing the data. After a disaster, there needs to be some mechanism to reconcile what you have lost with what is happening in the real world. There is a tedious reconstruction process of identifying what has been lost and manually keying in the data back in. That's one problem. Second problem is typically if you are doing data guard, then each application, each database has its own data guard session, And if it's, let's say, maximum performance mode, which is the asynchronous mode, and you get a disaster, you cannot guarantee that everything will be cut off exactly at the same point of time, which means when you bring the applications up at the remote site, each application will have data to a different point of time because there is no coordination between the different data guard sessions, and it creates a lot of problems if there are dependencies between the applications, and you want all of them to be in a same consistent state. When you are doing asynchronous replication, the decision to fail over is a very difficult decision because it dictates losing data. And there are many cases that one would like to fail over with the intention of failing back. If there is, for example, power failure, and there is a promise that the power will be back on in 2 hours. Typically, nobody would like to fail over. They would rather wait the 2 hours with an outage, because if they fail over, they definitely lose data. Now, if you don't lose data, you can fail over even for 2 hours, guaranteeing that you didn't lose, you are not down, and you can fail back safely because you didn't lose any data. So the decision of failing over is much simpler when the 2 sites are synchronized. You are not losing any data. And of course, the outcome of all of this is that the RTO, the recovery time objective of asynchronous replication, is significantly longer than with a sync replication, because you really need to reconcile data after failing over. The decision of failing over is longer, and the process takes much more time. So what did we do? What magic did we do to allow sort of a synchronous replication in an asynchronous world? So we have 2 solutions, one for 12C, one with 11G. Let's start with the 12C. So 12C, Oracle in 12C created a new replication mode, which is called the FarSync replication mode, where typically you have at a synchronous distance another FarSync site. It's called the FarSync site, that is sort of a hub of a data guard, that you do data guard synchronously from the primary site to the FarSync site, and then asynchronously from the FarSync site to the secondary site. And the FarSync site is basically a very thin server. It doesn't have all the database. It just serves as a relay between the primary site with the secondary site, with the intention that in those disasters when only the primary site fails, you can transmit the data that did not reach yet the secondary site, the standby site, from the FarSync site. This solution has, however, a number of drawbacks. So first of all, it's vulnerable to link failure. If for some reason the synchronous link fails, then the FarSync site will not be in sync with the primary site, and this situation occurs in many cases of a rolling disaster, where some communication relay on the way fails first, and then, say, an earthquake. So first the communication is lost, then the primary site is affected. Some power failures start not exactly at your site, but there is a failure of the communication first and then your site. In all those cases, the FarSync site will be out of sync. Then there is a vulnerability to regional disaster, of course. So in all those cases, there are many scenarios of disasters that primary site and FarSync site would be destroyed together, because if it wasn't the case, then there wouldn't be the need for a standby site at all. If people were sure that the parsing site would survive in all the cases where the primary site suffers a disaster, then it would have been enough to have the standby site at a sync distance, and this is not the case. And the third drawback is the cost of the parsing site. So typically, because you want to protect as much as possible the parsing site from a regional disaster, you want to put it at a synchronous distance for a primary site, but as far as possible from it. So you need another location, and you need communication lines, and you need to manage the site, and there are a lot of cost associated with managing that additional site in the middle. So Axxana has developed a box like a black box in an airplane, which means it can almost survive any disaster. And within the box, it has storage and a server. So it's very, very, you can call it a very, very resilient storage and a server box. It will survive direct fire for an hour. It would survive 6 hours of heat. Those two conditions typically characterize a fire in a building. It can drop on a reinforced concrete from 16 feet. It can sustain a crash force of 5,000 pounds. It's waterproof. It will survive a pierce force of 500-pound spear dropping from 10 feet. It has a self-sufficient power source, which means it has its own batteries that kick in case of a disaster. And it has an independent cellular and Wi-Fi communication means. So after a disaster, it's a totally independent piece of hardware that can continue operating after a disaster. In a nutshell, we call it a bunker in a box, with the advantage over a bunker that in a bunker case, in many cases after a disaster, the bunker will be cut off of the external world because the communication will not be working. And here there is communication after a disaster. You can communicate with the box through either Wi-Fi by having a laptop at a distance of, let's say, 200 feet, or a cellular when the cellular network is working. So how do we utilize this box? So in the previous example, if you have seen the far-sync communication with each drawback, what we do, we replace the far-sync site with our box, which means we run the far-sync instance within our box, where both the server and the storage are running in our box. And because the box is resilient to practically all of the disaster scenarios, it can run at a primary site very close to your primary server. So now what you're having a situation where the black box runs the far-sync instance. In case of a disaster that hits the primary site, the black box will survive the disaster, will switch from wireline to a wireless communication line, cellular line, and complete over data guard the transmission of all the data that is stored inside to the remote site. And of course, the data that it stores inside is basically only the gap between the primary and the standby site. It doesn't keep all the database. It keeps only the redo logs and archive logs that data guard transmitted to the black box or sent to the black box that did not reach yet the remote site. So replacing a regular far-sync server at a far-sync site with a black box that is running at the primary site You get resiliency to a link failure because now the black box is very near the primary server, so there is no case of a rolling disaster. It's very resilient to regional disaster. If the primary fails, the black box is designed to survive. And it's very cost effective because you don't need a third site for the parsing site. You don't need to put the parsing site at some distance for the primary site. You actually put it very close to the primary server. This is how some additional technical information. So during normal operation, as you see here, the black box serves as a regular parsing server. It connects over one running, it should have been over LAN. It connects over LAN to the primary databases running data guard in maximum availability, meaning in synchronous mode, and it connects over WAN to the remote standby databases running in maximum performance data guard, which means in async mode. When a disaster occurs, the communication to the secondary side is lost, to the standby side is lost, because in some cases that communication is not lost, but if it's lost, then the black box automatically switches to cellular transmission and transmit the data to the remote side using data guard sessions over cellular. And this part was developed together with Oracle because to run data guard over cellular created some challenges that we needed help from Oracle to overcome. As I said, in addition to that, we have the black box has a Wi-Fi connectivity, so if the cellular network doesn't work, you can transfer all the legs, all the data over Wi-Fi to a laptop, move the laptop to the nearest location where you have communication to the remote site, and complete the recovery from the laptop, again using data guard to the remote site. So this is the solution for 12C data guard. Now what do we do with 11G where parsing does not exist? So in 11G, this is the configuration. We do something a bit different, same principles, but a bit different. The black box is connected to the primary server as additional storage box, and we change the configuration of the database in the primary server to keep a copy of logs in our box by adding our additional member of the redo logs into our box. In addition to that, we create a new destination for archiving that is directed to our box as a storage. So basically, in normal operation, we keep within the black box synchronous copy of the redo log, plus archive logs that if the replication is data guard to the remote side, we know exactly which archive logs to delete after a while when they reach the remote side. So again, in our black box, during normal operation, like in 12C in the parsing, we have a copy of redo log, of archive log, and we also keep the control file, because the control file is essential for a correct recovery at the remote site. So again, we keep synchronous copy of the redo log, archive those archive logs that did not reach yet the remote site, and a current control file. In this case, the replication to the remote site can be either data guard or storage base. We don't care how the replication is being done. When a disaster occurs and everything is destroyed but our box, at the remote site, we have a component which is called a recoverer, which is just a server with some with software. It can be virtual machine that runs our software that basically pulls the missing redo logs and archive logs from the black box and hand them over FTP to the remote server. So when the standby server is brought up, it recovers using our redo logs and our copy of archive logs, again bringing the database to the last transaction. Again, we do a lot of optimization of what has to be moved. We basically are moving to the remote site only the transactions and the files that did not reach the remote site yet. We probe basically the remote, the standby database, and know what is missing there and what to take from the black box. Plus the fact that we have a mechanism for early identification of a disaster. So basically when the black box identifies that it lost communication with the primary server, plus it lost power and had to switch off to battery, it starts off on its own to transmit the data to the remote site, taking into account the fact that the decision to fail over is typically not an immediate decision. It takes time to fail over, so we are starting ahead of time transmitting the data to the remote site such that when a failover command is being given, we can have all the files ready at our recoverer at the remote site. If a failover is not initiated, then no harm is being done. We basically erase those files from the recoverer and operation continues as normal. So again, some technical detail. Data transport to the remote site here is done by Axxana. In 12C, the transport to the remote site is being done directly to the standby server using data guard. Here, since there is no data guard session from us to the remote site, we are doing it with our proprietary optimized protocols for cellular. As I said, there is a disaster auto detection mechanism, so we can start moving the data to the remote site ahead of the decision of a failover. And it works also with storage-based replication. We can connect also to Exadata with the previous, with 12C there is no issue with Exadata, non-Exadata, because we connect over data guard at the primary site. Here we connect as a regular storage, so there are 3 ways we can connect to an Exadata machine, either iSCSI over 10 gig, iSCSI over InfiniBand, or DNFS. Recovery procedure is certified by Oracle. So the recovery procedure with 11G is not straightforward. It needed to be certified by Oracle because there is a need to switch control files on the way. It's not just starting transitioning the standby to a primary and applying the redo and archive logs that we transfer there. There is also the need to replace the control file. And I'll go a little bit into details how this is done. It's all supported by scripts and CLI, so it can be done in manual mode, the recovery, and it can be done in automatic mode. You can initiate a script that will go through the whole process of recovery. And the recovery can be done over WAN. It doesn't have to be done over cellular. So in cases if you connect it to an Exadata, for example, and an Exadata itself has failed, power supply, something else, water was spilled over the box from air conditioning or other systems, and your primary Exadata goes out of commission, the communication to the remote site can be still done over WAN, much faster than over cellular, and you can transmit the data. By the way, with cellular, you can transmit about 6 to 12 gigabytes of data per hour, depends on the compression, on the type of the cellular network. We have battery to last for 6 hours of transmission, so you can calculate how much data you can transmit, and you need to understand that you are transmitting only the gap between the primary and secondary, which in most cases is measured in megabytes, not in gigabytes. So here is a brief outline of the recovery. How do you do recovery for 11G? As I said, for 12G, you don't do anything special other than the typical failover that you do with parsing. It's exactly like everything to do is exactly like parsing. We don't make any difference. With 11G, we do, because we are the one that are providing the archive and redo files to the remote site. So it consists of the number of steps. The first step is to transfer the data to the remote site, and this is a command that is initiated per database. It's Ax recovery command. It's called Ax recovery database. You say Ax recovery in the name of database, and this command runs over cellular transmission from the from our server at the remote site to the black box, and it transmits, it pulls all the data relevant for that database, for the redo logs and needed archive logs for that database, pulls them from the black box and store them at a location which is known for the standby database to do its recovery. Then you need to stop standby by doing alter database recover manage standby database cancel, and you apply the archive logs. So archive logs you can apply directly to the standby. Before applying the redo logs themselves, you need to change the control file. You cannot apply the redo logs the same way that you did with the archive logs. There is the danger of corruption. Also, as I understand, there are some users that are doing exactly that. They have some means to move the redo logs synchronously using storage-based replication to the remote site, and they are applying them at the standby. There are noted cases where it created a corruption if you don't update the control file. So here you need to replace the control file. This is the next step. You need to shut down, you need to shut down the database. You need to start it in a no-mount mode. You need to alter the control file. You need to shut down and start up in mount, and then do a crash recovery from the redo logs that are at the remote site. And by that way, you bring the database to zero data loss. And as I said, this procedure was certified by Oracle. Now this is the next slide here. It's a bit to give you some understanding what's inside the black box. So what you see here on the right bottom corner, you see the electronic parts that is inside. By the way, the electronic here is a bit crooked because this is the electronic that we extracted after doing a drop test from 16 feet. So basically what you see here are, just a second, what you see here is 4 disk drives. You see 2 cellular modems, so you can connect to 2 separate cellular providers to get a higher throughput. Here there is a place for battery that is missing. There is an electronic card behind that runs basically Linux. That's why we can run a parsing instance inside. And this electronics is embedded within a metal box which is waterproof, which is embedded in a cylinder that is designed to protect against penetration, against crash force, vibrations, and shocks. All this is protected in a special fabric material that protects against 1 hour of fire. By the way, because of problems with heat dissipation, because this electronics, everything is isolated from the external world, so there are problems with heat dissipation during normal operation. There is a small chiller that in normal mode chills the box and removes heat from inside. In a disaster, it's being destroyed, and the box is designed to transmit data for 6 hours without cooling. And on the upper left corner, you see the box, how it looks in a data center. Here you have some pictures of the test. So on the bottom left corner, you see the fire test. It's being done in a special furnace. There are only numerous labs that can conduct a test like that. It's a special furnace that controls the fire, simulates a fire in a building. You see how the box looked after 1 hour of fire. On the right-hand side, this is the heat test for 6 hours. Then there is a load test, waterproof test, penetration test. On the lower left side, you see the spear that is being dropped from 16 feet. You see the damage that it did to the cylinder. There was a dent in the cylinder after the drop, but it didn't damage anything inside. Then on the right-hand corner, you see the vibration test and shock test, etc. So here is a small exercise of sizing. How do you size how many databases you can protect within a single box, to how many servers you can protect. So assume it's a 4-node rack configuration, and each redo file is 5 gigabytes in size, and there are 6 groups, and the maximum throughput is 100 megabytes per second, and the average throughput is 20 megabytes per second. So our sizing is basically done on space requirement within our box and on the throughput, the sustained throughput to our box. There is a maximum throughput that we can sustain, and we have a limited space. So we'll talk about the models that we have, but basically what are the space requirements. So the minimum space that you need is 120 gigabytes. This is just to protect the redo file. So if you your asynchronous replication is near synchronous, since you have very good lines, you are running in maximum performance, but the gap between the primary and secondary is smaller than the total size of your redo logs, then you need 120 gigabytes to protect all your redo logs. The worst case protection that you need is 120. So in the worst case, in worst case, the number of minutes you would be protecting is about 20 minutes. This happens when you are protecting 120 gigabytes and you are running at maximum throughput of 100 megabytes per second. So this buys you 20 minutes of protection. So in many cases, this is enough for all practical purposes if you don't want to protect also against the case where your link fails first and you would be accumulating larger gaps, larger legs. The average protection leg is 120 divided by 20 megabytes per second, and that gives you, on an average, you would be protecting 1.6 hours of data. And if you want to protect 6 hours, for 6 hours, there are some customers that are claiming that they may have an outage of their link for 6 hours, and they want to protect a leg of 6 hours. So you need to have, so you would need 432 gigabytes of storage within our box. It's basically 6 hours, which is 3,600 seconds, times 6 times average throughput, and this gives you the amount of gigabytes. And the required bandwidth to the box per database like that is 100 megabytes per second, because you need to guarantee a maximum throughput. So bearing this in mind, we basically have 4 models of boxes with different capacities and different throughputs. So the low-end model, we can protect 8 gigabytes of storage, and the throughput is 800 megabytes per second. So if this is the box, then we can, based on space, we can protect 6 applications, because you need per application 120 gigabytes. So in 800 gigabytes capacity, you can protect 6 databases like that. Based on throughput, you can protect 8, because you need 100 megabytes per second per database, and you have 800 megabytes per second. But of course, the bottleneck would be the space, so you can protect 6 databases. If you want to protect a database for a leg of 6 hours, you can protect only one of those, because you need 462 gigabytes for that. So you won't be able to fit 2 of them into one box. The next box that we have has 1.6 terabytes of storage running at 800 megabytes per second. And again, I will not go again through that calculation again, but basically you can protect 8 databases like this. And here the bottleneck would be the throughput, because from the space perspective, you have much more space than in the previous box, so you can protect more, but you are limited by 800 megabytes per second. And if you want to protect for 6 hours, you can protect databases. The next model is 1.6 terabytes and 1.6 gigabytes per second, and here you can protect 13 databases. And the high-end model is 3.2 terabytes running at 1.6 gigabytes per second, and you can protect 16 databases, like with the characteristics that I've described. So basically, to sum up, so we are providing a solution that is, I hope I convinced you that we are providing a solution that is zero data loss, 100%. You will not lose anything. It overcomes distance limitations because the standby can be at any distance. It protects against link failures, which in many rolling disasters, that's what happens, the link fails first. And it also provides application consistency because once you bring all applications to the last transaction, then you didn't lose consistency. All applications are consistent by default. So with that note, I concluded the presentation, and thank you very much, and I'll be happy to answer questions.
At this time, it doesn't look like we have any questions, but please do feel free to use that question and answer chat box to submit any questions that you have for Dr. Winokur. And while we give everyone a few minutes to submit, any last-minute thoughts or closing items you'd like to share?
You mean by me?
Yes.
As I said at the beginning, it's a very unique solution. I don't think there exists any other solution that can provide protection like that over any distance without going any distance, with using regular communication lines that don't need to be very high performing. In that sense, it's really a unique solution that did not exist till now.
Great, thank you. We've had a few comments just thanking you for your time and saying that you've done a great presentation so far. If there are no other questions, we can go ahead and conclude the webinar. Please do feel free to submit any follow-up questions to the speakers at ioug.org inbox, and we can follow up with Dr. Winokur and get those answered. At this time, I'd like to give a big thank you to our speaker today. Before we conclude, please make note of our upcoming webinars and past webinars by visiting www.ioug.org. A recording from this presentation will soon be available on the IOUG website and our Resource Center. We'd like to thank our speaker, Dr. Winokur, and everyone online for attending the event today. There is a survey that will populate after this webinar. We thank you in advance for your feedback. Thank you again for attending and have a great day.
Thank you.